All right. So, welcome everyone. This is the first high energy seminar of the semester, and we're very happy to have Nick visit us from IU. He did his PhD at UIUC, working with Marius Junge on operator algebras. Then he went to U Chicago for a postdoc, and then since last year, he's been at IU.
Actually, 2 years.
2 years ago. Time flies. As an assistant professor, and he will be telling us about new state of unitary K designs. Please.
All right, thank you. So, first, what is a unitary K design? Well, on a d-dimensional quantum system, we would think of the unitaries as modeling quantum processes, and the unitary group admits a bar or uniform measure. So there is a notion of what it would mean to, say, take a uniformly average random unitary. Random unitaries show up in a variety of places, such as in quantum information theory. They're actually used as information encoding against errors. In quantum complexity theory, some of these random circuit sampling experiments use these. And probably most importantly to this audience, as models of quantum chaos and related phenomena, such as black holes that are potentially governed by random matrix theory. So there is, however, a problem with generating random unitaries. Actually, having that because now I can see my own slide without having to look there.
That's good. That's good.
And that comes from a pretty old counting argument that you can actually find in some of the original textbooks on the field that says that there are about 2 to the order of n, maybe polynomial of n, ways to describe a quantum circuit, or really to index or refer to a quantum state or process using n bits of information. But in an n qubit space, there are doubly exponentially, or exponential in dimension, many ways or many quantum states that are approximately distinguishable up to some fixed error. And so what this implies is that most of the quantum states on an n-qubit space must be exponentially complex to actually even write down a description of in any kind of description language. And of course, this means they're also complex to prepare, complex to derive from a physical process. So if I have some physical system that's time evolving, I would actually expect it to need exponentially long times to generate sort of a typical state. Now, a possible solution to this is to study states that are not distributed close to uniformly in a measure theoretic sense, but resemble uniformity in an observable sense. So this naturally brings us to the notion of a K design. And a K design is a distribution on the unitary group that looks uniform to an observer who can draw a unitary and test it K times from that distribution. So we might consider them to have sort of a black box. The black box will pull a unitary, and they get to use the same randomly drawn unitary K times over, apply it however they would like. And we would say it's a K design if it would be difficult to distinguish this from if the black box were drawing the unitary uniformly. So all of the observable properties kind of have to match what a typical unitary would look like. As a more formal definition, I actually want to recall the notion of the completely positive order or Louvner order on channels. And what this in mathematical terms says is that for quantum channels phi and psi, if 1 minus epsilon phi precedes or is less than psi, that's equivalent to saying that psi minus 1 minus epsilon phi is positive, completely positive. And for more physical terms, I would actually think of it as psi being a convex or probabilistic combination that involves phi. So I could actually think of psi as the result of, with 1 minus epsilon probability applying phi, and with epsilon probability applying some other quantum channel. For a little bit of context, quantum channels in general are completely positive trace-preserving maps. Here, though, we are interested really in a particular form of quantum channel, which I would call a k-fold twirl. And that is where we draw a unitary from some measure mu and apply k tensor copies of that unitary to an input state, or in this case, a density matrix if it's finite dimensional. So we call a measure a design in two different senses. We have diamond norm, or additive error k designs, as they're called in the literature, which simply says that for some epsilon approximation, the k-fold twirl is close to the Haar twirl in the diamond norm. And we would call its distribution an epsilon approximate relative error k design if it is comparable in both directions with some epsilon factor to the Haar or uniform twirl as well. See a few people taking photos. Any questions at this stage?
So what you're saying, does it matter for you that these are trace-preserving maps, or you could work with unital CP maps equally as well for the rest of your story?
So if you're applying these to density matrices or to states on finite dimensional von Neumann algebras, they should be trace-preserving so that they preserve sort of the normalization. If you're applying these to observables, you would actually want the unital CP maps.
Right.
So that would be probably in a mathematician sense the more normal thing to study. These are dual to each other.
So for example, for non-matrix algebras, you would be looking at the Heisenberg picture.
Yeah. And I mean, this is a little bit more tuned to the physics audience for today, but yeah. So these have been studied since roughly the mid-2000s in a quantum context. The idea of a K design, I think, actually goes back further and applied more generally. You can think of spherical K designs or orthogonal K designs. And it was in these first few papers on sort of mid-2000s that people said, actually, these would be interesting to look at in the quantum setting in pseudo-randomness context. So people were interested in pseudo-randomness, which is a huge thing in classical computing theory. And you could say, well, a K design is like a pseudo-randomness for quantum. And then there was kind of a wave of papers that showed that these are efficient, or at least tractable to construct. So within polynomial depth, you could create ensembles of quantum circuits that would form K designs. And of course, that's a big jump from the exponentially deep circuits you would need to make truly typical uniformly distributed unitaries. And then people were chasing this goal of showing that if you have n qubits and you want a K design, the depth should be about nk. And that was considered like the big thing then. There was some thought that maybe if you have like a very well-connected graph, in some notions you could do it faster. But at least in sort of a one-dimensional kind of minimal connectivity picture, it was thought that you would need nk. And then there were a few papers as of 2024. One of these is mine with Felix, where we showed that, in fact, you can do it in depth that's logarithmic in the qubit. And so that was considered very surprising. And a few papers have built on that and shown that if you have lots of structure and auxiliaries, you can do it even shallower. But so why was that so surprising? Well, if you went back to spring 2024, you might have seen this argument that you would need depth that should be at least enough for information to get from one side of the system to the other side of the system. And so if you look at this, for example, on a one-dimensional lattice, where you have nearest neighbor connectivity, then the depth that you need should roughly scale with the number of qubits or qubits that you're acting on. There was also some earlier work that looked at what it would take to get exponential precision and showed that for exponentially precise errors, you would actually need to have extensive entanglement. So this was sort of formalized as a couple of open questions in this paper of Arrow and Maribon, which was the state of the art on designs for a while. And they basically said two things. One is this: does this light cone argument actually apply? Can you show this rigorously that if you have a lattice in dimension capital D, spatial dimension, not Hilbert space dimension, then the depth should scale something like n to the root of 1 over d, because that would be the length of a diameter from corner to corner. And they also asked, is it possible to construct these relative error K designs using sublinear depth at all in and the qubit number? So these were, of course, resolved in 2024. I'm sort of highlighting the result I had with Felix, although the other result actually is stronger. So we both ended up resolving this concurrently and showing that given a certain slightly structured circuit ensemble, so not just any old random circuit ensemble, but a random circuit that we've configured in a particular way that is still defined on this limited architecture with one-dimensional nearest neighbor connectivity, you can get an epsilon approximate relative error K design in depth log n plus log 1 over epsilon, and then with some K factors.
So I understand that these are rigorous results, but what went wrong with the physics intuition of light cone, or like say Lee Robinson type count? What goes wrong over there?
Yeah, so why isn't it constrained by light cones? The way I have a couple ways of describing what I think happens, and one of them is that very quickly you get a lot of mixture, and you get a lot of mixture, especially when you look at the local level. And so you're looking at these very high entropy states. And so if you try to sort of do the kind of local tests that are going to distinguish light cones, you're mostly just going to find that you're getting very mixed states. And when you're looking at states that are already very mixed, it can often be hard to tell that those states are not actually uniformly distributed. So like if I'm doing local measurements, even within a fairly shallow depth, and instead of getting like bit strings out of the measurements, I'm just going to get a bunch of bit strings. I don't have any like predefined way of computing what they should be, and they're all going to look different from each other. And that's totally consistent with white noise. So you need a lot. I mean, it's almost in that sense probably the same reason that random circuit sampling is very hard to verify that you're actually doing random circuit sampling. This is kind of one of the known caveats of the random circuit sampling experiments, that you need extremely high computer power and a large number of samples to actually be able to tell that a random circuit sampling experiment wasn't white noise. Another way I would put this is that, so you could compare it to kind of these like permutation generators. So you could think about, instead of generating unitary group, you're just going to move things around the n qubits. And I think that to create like the permutation analog, where I'm just swapping the n qubits kind of independently from this k-fold structure, the light cone intuition probably would hold. And the difference here, when we actually use the full unitary group, which you can see in the k equals 2 case a little bit more rigorously, is that it's kind of like we have things that are moving bits of information around, which are local, but we also have things that are taking a 0, 0 to a 1, 1, and a 1, 1 to a 0, 0. So we have sort of a pair creation. And that pair creation makes it, again, very hard to test for locality. And I could go into more detail on that in the end if people want. I could actually start to draw out some of these arguments. Yeah, so we got this result, and at the same time, it turns out that Schuster, Haferkamp, and Huang were working on this and got the same n dependence, but they managed to get the k dependence to be 1 factor better, which turned out to make a big difference. So ultimately, we were working on this concurrently, but they were sort of ahead of us in that way. How does this actually work, though? How do we get this? So the intuition kind of started by thinking about this as a communication problem. And I would say, what if we have two parties, Alice and Bob, and they want to construct unitary designs, but they want all of the joint, and they want to do this on a joint system. So we have a system A, tensor product B. They want designs that are global, but they want the unitaries in these designs to minimize the amount of communication. So we started studying this protocol in which they each respectively perform local twirls. So remember, these are unitary averages. And maybe they do sort of uniform ideal local twirls. Then they do some kind of an information exchange. So maybe a joint twirl, or maybe they swap some qubits. Turns out it doesn't matter that much which one they do. And then they do another round of local twirls. And you could ask, is the entire system now a design?
Sorry, you're allowing for quantum communication as well.
Yeah, it is quantum communication. So they are exchanging qubits between the two. And we're asking, does this work? And if so, it does work, how much communication do they actually need? And the big initial result was that they need a number of qubits exchanged that scales with k and epsilon, but not with n. There is no n dependence here. And in fact, it doesn't matter how big the A and the B systems are. So this was a bit counterintuitive, but we were able to show this pretty rigorously. And this sort of formed the base of what's going to come next. So more explanation. Why does this actually work mathematically? A few of the tools we used. One of the standard ways of comparing distances in quantum information theory is what we often call the spectral gap. And I will warn you that there are 4 or 5 different things that they call the spectral gap. And they are related, but sometimes they're not the same thing. But this is often referred to as a spectral gap. It is a superoperator 2 to 2 norm based on the Shatton 2 norm. And what we could do is model this protocol as applying these local twirls given by the operator P, and sandwiching a swap Q SW in between those local twirls. And we can then study what's called the subspace angle, which was a concept introduced by von Neumann, which is this spectral gap between the composition of the two of these projections. And you may notice these are in fact projections, this QSW and this P, and the projection to the intersection of the subspaces they project to, which is this R.
Sorry, for this E to be limit of n going to infinity phi n, that does not hold for, that holds for certain channels, right? It's not like you can take a channel and just, right, like a unit.
So not every channel has a spectral gap. That's true.
Oh, you're saying that.
Or sometimes it's a trivial spectral gap, it's one.
If a channel has spectral gap, then phi to the power of n has a limit of n going to infinity, which is equal to projection to the.
Yeah.
Okay, that's what you said. Thank you.
I mean, it always has a limit, but the spectral gap is like how quickly it's converting.
What doesn't always have a limit? The unitary rotation in phi dimensions. There's no limit, right? Just keep rotating.
Yeah, you can.
Oh, but it's positive.
It's a channel, right?
Yeah, so a unitary, what you would actually do with a unitary is, I think, replace the fixed point projection by a decoherence-free subspace projection, which is the subspace on which it acts invertibly. And once you do that, it's sort of trivial again. It's already in its decoherence-free subspace. But
for general channel, you would just do the von Neumann projection 1 plus phi squared plus phi cubed to phi n divided by n limit of n equal to infinity.
that gets you a different thing. So that's another way to do it. But
okay, so, yeah.
For studying designs, it's actually the easy case, easy in quotes, because we actually do have a fixed point subspace. It doesn't do any sort of persistent rotations. So we can just not worry about that issue. So what are the next steps? Well, one of the nice things about studying subspace angles is that we can actually rewrite these in terms of Hilbert-Schmidt inner products. So we look at these projections and we look at the subspace angle, and this actually looks like we're doing a sort of inner product space here. And how do we calculate it? And that's where Schur-Weil duality comes into the picture. So there is this very nice idea of unitary representations of the symmetric group applied to the K copies that exchange the copies, and unitary representations of the K-fold unitary group that are illustrated in these two below that apply the same unitary K times. And you can decompose the Hilbert space as a direct sum of an irreducible representation of the K-fold unitaries tensored with an irreducible representation of the permutations. And so it has this kind of nice decomposition structure. And you know that the K-fold unitaries on each of these sort of blocks is only acting on the unitary irrep. Conversely, the K-fold permutations are only acting on the permutation irreps. And that leads for operators to another kind of nice way of writing them. And this is where we actually get into finite dimensional von Neumann algebras. So we would think of the state or space of operators here after performing a unitary twirl as having this kind of diagonal block structure where each of these blocks has a multiplicity that is induced by the unitary twirl. And we would also think of operators in this space actually being writable as a sum over permutation representations. So if we have an operator that commutes with all of the unitary representations, it must have this form. And now we would go back to our setting with the bipartite local twirls and decompose the operators into these permutation representations. And we can calculate these inner products that we need to get the subspace angle approximately all in this kind of new permutation vector space. So we started with these operators that have this sort of k-fold unitary structure as well as this permutation structure, or that we're on this space of something that's exponential in both n and k. But we're saying that once we write the operators in this form and actually examine this inner product with up to some Graham matrices that are close to the identity, it looks like we're just doing vector inner products where the vectors are the coefficients of these representations. And so a lot of this actually came from something that Aram Harrow had known for years and used in that earlier paper with, well, some of those earlier papers, but finally written in a self-contained way in this 2023 paper. And so that's what allows us to say these GA and GB matrices are close to identity, and therefore, approximately, this is just the vector of the product. And crucially, what that means is that we're kind of forgetting all of the structure that was in those unitary irreps. Like we're only going to remember the k-fold permutation representations of operators. And so we've reduced calculating the spectral gaps to calculating these inner products, and that's in an effectively much smaller space. It only knows about this k-fold permutation information. And then we would ask, okay, but that's for spectral gaps. Relative error is a much more ambitious notion of convergence. So the usual way, which will not suffice, to go from spectral gap to relative error was also noted in an earlier paper with Aram Harrow. And this basically says that if you know, this is another kind of version of something that looks like a spectral gap. If you know that this inequality holds, then you can multiply things by some factor of the entire space dimension squared and bound the relative error comparability. And in fact, in the 2010s, when this paper was written and some of the others, this was the standard way to do it. You calculate the spectral gap, and then you take that channel n times, which amplifies the spectral gap, until you get this to q to the n, or maybe nk times, so you get a 1 over q to the nk in the amplified. And then you do this conversion, cancel that, and get depth that is lower bounded by nk. Using the block structure, however, we can potentially convert between norms more efficiently. So in reality, you don't really need the full system dimension. What you need is something that is actually very much like a von Neumann algebra index. You can actually do some of these conversions with the Pimsner-Popa index, if you're familiar with that. And in our case, remember that after we did this bipartite local twirl, we sort of canceled all of the unitary irreps out. Those are all multiplicity subsystems. we're left with arreps of the k-fold permutation group, but there's only potentially k factorial dimensions or ways to permute something that has k distinct sites. So the only effective dimension that's coming in is something that's polynomial in k factorial. So once we do that, we're basically able to perform this norm conversion, but instead of a q to the 2kn, we get some poly k factorial here. We go to relative error without putting any factors of n back in. And then what we would do is actually apply this bipartite protocol to small chunks that are size log n of a large system. And we would merge neighboring chunks, and then we'd merge chunks, and each time we're having the size. And that looks like it would introduce a logarithmic depth factor, but it turns out that you can do these more parallel, so you don't actually increase the depth doing this. We could do the same thing on higher dimensional lattices. We can sort of take subblocks and combine subblocks. And here it's a little bit more illustrated. What we really would think of doing is each of these white squares is one of our sort of initial chunks. And then we would apply these joining operations that bind them together. And this whole thing would look like a K design. So as a consequence, not only do we get log n depth, we also get log n entanglement entropy up to some small corrections. Or more broadly, given an area or a sort of a subsystem drawn with any sort of arbitrary boundary, we get approximately area law entanglement for K designs, even though for uniformly random unitaries, the entanglement would almost always be volume law. So what did Schuster, Haferkamp, and Huang do differently that let them improve the K dependence a little bit? They actually never really went through spectral gap as far as I can tell. They sort of had a more direct norm conversion that came from starting with Weingarten calculus on the random matrices. They managed to get rid of one more factor of K sort of very early in the game.
Sorry, sir, but the basic intuition, which was based on this communication between Alice and Bob trying to prepare a global random unitary grid by communicating, is that the same idea in their work as well?
That idea isn't, so you can actually get that idea from what they did. So you can derive it. They didn't really start with that picture though. They started with kind of like you have overlapping twirls and just directly calculating that convergence to a global twirl. And however, if you look at it, you actually do see that their main lemma, which they call the gluing lemma, effectively is saying that this is the amount of overlap between the twirls that you need to give you good convergence to a global design. And so there is a communication picture kind of a little bit more.
Another way of answering the question is that starting with the intuition of this communication problem, can you basically reproduce their result with one less factor of K?
Yeah, I think you can. So these K log Ks actually come out of just taking the log of the K factorial. Again, these are the results that we get. So what's actually new from this? Remember, this was in 2024. I want to sort of spend maybe if there are more questions, I can take questions now. But I want to get on to what's happened since.
I have one very naive question. So in this communication task, the key idea was that the amount of quantum communication required is independent of n, right? So now let's say they have matrix algebras. Can I play games of taking some sort of a limit of matrix algebras who have this for other three-dimensional one-dimensional algebra, say type 3 tensor product? Can I play these games? Because you're saying that the result is independent of n.
Yeah, so presumably, if you're doing the bipartite communication strategy, you should be able to take the infinite dimensional limits. And
for hyperfinite.
Yeah, so I guess you could try to glue two hyperfinite factors
with
a finite dimensional glue, which is weird to think about, but technically that should work. Haven't checked it, but yeah.
It would turn it into a field theory example.
Yeah, the reason why we get log n's in here and not a constant depth is actually that when you start doing these recursive schemes, you get some like constant error every time you do a block merge. And you build up n of those errors because you're eliminating n boundaries. And so you need the block to have errors that look like 1 over n so that you cancel the n's when you add them up. So that's where the n comes from, but the bipartite thing, yeah, there's no n dependence. It could be infinite dimensional. So what's next from here? Well, there are some standard architectures that are studied as kind of like physical models, or that's what they might think of as not very structured models. And one of them is what they call one-dimensional brickwork, where you're on a one-dimensional nearest neighbor line, you pair off the neighbors, apply random gates to the pairs, and then you pair off the neighbors the other way. So like first you're pairing 1 with 2 and 2 and 3 with 4. Next layer you're pairing 2 with 3 and 4 with 5. So you alternate between these pairings, and that's something that should converge to a global random circuit. Another way of thinking about this is you, at each step, choose a random edge and apply a random gate to the corresponding to subsystems, where subsystems are kind of placed on some arbitrary connectivity graph. So this is in some ways an even less structured model. We're saying there's some notion of connectivity, and there's some random process that's sort of randomly interacting these. It could be thought of as sequential, but you could also think of it as sort of like, I think what's called a Poisson clock, where these can kind of happen effectively in parallel and not really interfere with each other. So what do we do in these papers? Well, again, to do this recursive build-up structure, we need to kind of split the brickwork into chunks. So each of these chunks would be log n width and log n depth, and we have 2 chunked layers. And so it almost looks like we're repeating a brickwork layer, but at a bigger scale. And at first, there was some thought, well, okay, this is probably just a technical distinction. You know, they'll show that it works for brickwork early on. And then a year went by and no one had shown that you can get rid of these kind of barriers replacing through the brickwork that are actually cutting out gates. And actually some colleagues at UIUC, Daniel Belkin, Brian Clark, and maybe, forget whether James Allen was also on that paper, or maybe someone else, showed that adding random 2-qubit unitaries to something that forms a design can slow down its convergence. It was called something like absence of censoring inequalities. And so that showed that it wouldn't necessarily be free to kind of reconnect things in the first chunk layer by putting back in the mids and gates. So I don't know, the colors are not displaying that well, but you might be able to see that like this gate is blanked out, this one is blanked out. We had to take a bunch of gates out to impose this structure. It's not assured that putting gates back in will speed things up. It could slow things down in principle. So the next sort of result was actually showing that at least if we're willing to bend a little bit on the notion of decay, we can patch this back to brickwork, or possibly back to the random gates on graphs model. And how did I do that? Well, this actually goes through the quantum relative entropy. And so this has a sort of nice infinite dimensional version defined by Araki, and there's the original Umegaki version that uses a trace. But this has a bunch of nice properties. It is monotonic under applying channels to both arguments. The argument should be states or densities in finite dimension. It has a chain rule. So if you take it with respect to a conditional expectation, you can, on a different state, you can rewrite this as the sum of the relative entropy to the conditional expectation plus the relative entropy to that state in the subalgebra. It's additive on tensor products and superadditive in general. And Pincer's inequality says that it upper bounds the trace distance. So that can be operationally useful. This has been studied a lot in quantum information theory. These are actually some slides from Mark Wilde's talk many years ago, showing, sort of noting that the decay or decrease of quantum relative entropy, which we could think of in many contexts as being analogous to a growth of Shannon or von Neumann entropy, comes up all over the place. So I want to emphasize this data processing inequality because much of the recent work has been looking at what happens when we strengthen it. And in fact, this is what we might call a strong data processing inequality. Not only is it not increasing under application of a channel of both arguments, but for some channels, and this is channel dependent, we would be able to say that the relative entropy to a conditional expectation has a contraction coefficient. It gets smaller by some factor. And we can strengthen that even a little bit more by saying this would hold under all extensions under auxiliary systems of the same type. And a lot of people worked on this. You've already seen that, I think, CP order. So in a few years ago, I worked with Marius Junge and Li Gao and Haozhan Li on this. And we came up with a very useful theorem which says that if you have, in the long time limit, decay in this relative error sense, which is a very strong sense, then a single application of the channel will actually give you a sort of proportionate CSDPI constant. So relative entropy contraction is in many ways weaker than relative error, but it does have this advantage that there's this long time to short time conversion. If it eventually converges in relative error, then it must start relative entropy decay right away. It can't kind of wait until late times and then start falling. And another theorem that has not been as much in the literature, that is kind of an underpinning of this new work.
Sorry, can I ask this a very basic question? So naively, I'm under the impression that this relative entropy strength inequality with lambda in it is stronger than existence of a gap. Is that correct? Can you show that this always implies a gap?
So this does always imply a gap, and I think the conversion from this to a gap is very efficient. So I think it might even have to have like a gap with the same coefficient. The conversion the other direction is not necessarily efficient.
Because if you know there is a gap, then relative entropy has to start decaying.
Yeah, but it could decay much more slowly than the gap. So this is in some sense stronger, quantitatively stronger than spectral. The other thing that turns out to be very useful now is that, say you have a sequence of channels and they all have this CSDPI contraction coefficient, and their fixed point projections all converge or compose in a way that in relative error is comparable to the intersection subspace, then you get a DPI constant for the composition of the channels. So this is sort of like an entropy decay recombination theorem. And there's actually a bunch of variants of this. But what do we do with this? Well, I want to reanalyze this slightly structured ensemble that almost looks like brickwork using these relative entropy bounds. And so here I'm actually going to color the different chunks. They're all applying different k-fold independent random unitaries to 2 qubits, but the colors are sort of showing you just which chunk they're in. So they start to be meaningful because using this long to short time relative entropy decay theorem in combination with the recombination result, we can effectively flatten out the chunks. So we can say, if this thing converges in relative error, which it does by the 224 results, then if we just take a pair of layers from each and compose them, that has to have CSDPI. And then by data processing, well, we're always allowed to prepend and append channels, and that doesn't break CSDPI. We can fill in the holes, and we can get back to one-dimensional brickwork. And it turns out that this is actually in some ways more immediate if you're looking at this random gates model. I'm not going to go into much detail there, but if the gate placements are random, you can effectively just pick an order and therefore jump to whatever structured scheme you like pretty quickly. And so this is the main outcome then, that if we take something like 1D brickwork, and there's a bit of a generalization to more higher dimensional lattice brickworks, or if we take this random gate model, they have 1 over k polylog k log n CSDPI towards k designs. And so this is a destructuring theorem. It says that actually, at least the relative entropy decay is fairly general for random circuit architectures. You don't need a lot of specific partitioning and block arrangements. As you recall, because of Pincher's inequality, you can actually get diamond norm convergence. So I know that quantum info theory, diamond norm is often thought to be the operational thing. And so this yields shallow designs that are more general. Very preliminarily, I think actually these logarithms can be improved. And this is a very preliminary thing, but you can kind of do things recursively where you break down the logarithmic blocks into their own, like log n blocks, and then you break those into log n blocks. And so you can kind of recursively apply this and possibly get something smaller than the logarithm there. I think even the iterated logarithm. This is coming very close to lower bounds on the diamond norm. So this is getting very close to tight for probably both diamond norm and relative entropy. Another nice thing you can do with this is that relative entropy decay is again very divisible. Like just a little bit of random circuit in a relative entropy decay sense must induce a proportional amount of decay. So if you examine some very arbitrary circuit or arbitrary ensemble and you inject random gates, say you're modeling a quantum computer with imperfect controls, you will still get a K design. It doesn't really matter what's interrupting it, unless that interrupting thing is creating purity. So you can't, for example, forestall K design formation by inserting more unitaries. And so this is actually recovering something like a censoring inequality. It's saying that putting more gates in this sense, doesn't make things slower. And so where are we now? I'm just going to kind of wrap up. I would say that log depth is probably becoming the standard sort of, that's where we expect K designs to happen. If you are willing to add more qubits and extra structure, there's another paper, these are all by other authors. You can get actually faster convergence with a lot of caveats. There's also some results now for Hamiltonian ensembles and for stronger notions of designs than the relative error represented here. Where are we looking? Well, I'm looking at sort of how architecture independent is this really? I think that you should be able to get relative error log depth for a lot. There should be some very general criteria to say, okay, this ensemble is going to give you relative error log depth. Also how measurements interact with K designs. And I think there's a whole bunch of new questions that are sort of just maybe coming into mind. But yeah, I'd like to acknowledge particularly Nima and Kristen for bringing me here. I worked with this. The first part was co-authored with Felix. The second part, I talked with Felix a little bit about it. Also Nick Hunter-Jones, the student Siobhan, and Daniel Belkin at UIUC. I want to thank you for listening. So
much, Nick. Are there more questions?
Yeah.
I have a question about the later part where you have this orange.
Oh yeah. Okay.
Yeah. So what are the gray gates again?
So in this case, what I'm imagining is that the gray gates are actually something pretty arbitrary. I said non-random in this picture. I think the original picture I had in mind was, say you take something like Shor's algorithm on a quantum computer, and that has kind of a relatively fixed architecture in terms of gates. It's not random, but on many quantum computers, you'll have some control errors. So the gates you actually do and the gate you programmed in are not exactly the same. You get maybe some small chance that it does insert some randomness, including crosstalk between qubits. And so I could think of that as being the orange gates, that every once in a while you get this spurious interaction. It doesn't have to be a uniform or strongly random thing. It can be even something that's just a little bit of spurious interaction between neighboring qubits that's kind of uncontrolled and therefore random. That will induce K-design convergence. And so this, I suspect, is going to lead to either new barrier results or maybe a deeper understanding of our earlier barrier results to quantum algorithms either on kind of noisy physical hardware or on parameterized circuit ensembles potentially. Because what we're seeing is that it's really, really easy to make a 2 design. In fact, it's so easy to make a 2 design if you put a bit of randomness into an algorithm or let it sneak in, you're probably going to do it by accident. That's what I suspect. And so you look at a lot of these quantum optimization algorithms, they're probably unintentionally making 2 designs. And that's likely a barrier result because the outputs of a 2 design look like uniform randomness. So what you're measuring out of it would be difficult to distinguish from white noise. So unless you're a cryptographer trying to make very good secure randomness, you probably don't want to make 2 designs in your algorithm.
So you're questioning the stability of these algorithms to noise.
Stability to noise, and also kind of like, again, there's this whole like little subfield of parameterized algorithms that have some variability over the parameters. And like barren plateaus, if you've heard that phrase, it's probably easier to make barren plateaus than people imagined.
Any other questions? I do have one last question. So this communication statement, which seems to me to be the core result, but Alice and Bob they need at least they need an amount of communication which was independent of n. But because you got that other short while duality, it gives me the impression it's probably optimal, meaning that they need at least that much communication.
So,
is that true?
Yeah, if I go all the way back to that thing, where is this?
So with short while duality, we often can prove optimality.
So I would say that the n dependence is optimal. You can't do better than constant. The k dependence is not optimal. And again, if you look at the Schuster, Haferkamp, and Lang construction, and you adjust it a little bit, or you read it as a communication thing, which I think is a perfectly valid reading of it. It wouldn't be k log k here; it would just be log k.
Mm-hmm. Yeah,
and that must be tight.
Yeah. Okay. Good. Very good. All right. Let's thank Nick.